It is my honor to introduce to all of you Professor Aubrey. He's a distinguished physicist. I know his contribution to string theory and quantum gravity very much. That is the reason why he receives the award, Benjamin Lee Professorship, in this year. He will give his talk, and the title is Constraints on Quantum Gravity. I hope all of you will receive a chance to read his perspective on quantum gravity and string theory. Please, Hiroshi, show us your perspective.
Thank you for the kind introduction. I'm overwhelmed by this wonderful award ceremony, and it is my great honor and pleasure to give this year's Benjamin Lee lecture. So please allow me to share my slide, and I hope you can see it now. Yes, okay, good. So once again, it is my great honor to deliver this year's Benjamin Lee lecture. And so I understand that except for Professor Gerald Tucht, probably my area of research is closest to the one of that of Professor Lee. So I thought that before I begin my lecture, I thought I should say a few words about Professor Lee himself. So I cannot do, I think the best I can do first will be to quote from the speech that Xian Yang read in the memorial in honor of Benjamin Lee held in 1977. Xian Yang is a Nobel laureate, and he was also the first president of APCTP. So in this speech, he cited two works of Professor Lee. One is this famous work on property of J-psi particle before it was discovered, and the other is a renormalization of gauge theories. And on the latter things, the renormalizability of gauge theory, Xian Yang point out that we know that few contributions in theoretical physics remain noticeable after 10 years, fewer after 20. I venture to guess that the renormalizability of gauge field will remain important 50 years from now. And well, we are already 44 years after this speech, and renormalizability of gauge theory is as important as ever. So this prediction is certainly realized. Talking about this work on J-psi, there is actually a very nice autobiography by Marie K. Gaillard. She was my colleague at UC Berkeley. And she actually, in this autobiography, she remembered her work with Benjamin Lee on J-psi particle. And so here she tells us how this work came about. We decided to investigate in detail the way in which production of charm particle could be detected. But she also pointed out that atmosphere of his group at Fermilab was remarkably accommodating and inclusive for female scientists like her. She said that the year at Fermilab marked an important turning point of my career, which was perhaps enabled in part by the absence of the rather patronizing attitude toward women that I had encountered in Europe. And she went on to say that that year also led to a close friendship with Ben and his family. So she really appreciated her the Benjamin Lee's mentorship of her during her time at Fermilab. This honor is very special for me because it is actually his physics report review article and his famous lecture note at the Regius School that I learned the modern quantum field theory, in particular, how you quantize a gauge field. I believe this is a photograph of Professor Lee. As we all know, unfortunately, he passed away during his trip to Aspen Center for Physics from Chicago. He was a member of a trustee at that time. And so I was actually there this summer. This year, I was elected the chair of the board of trustees. And so I took this photograph. This is the actually only memorial on the campus of Aspen Center for Physics for physicists. And so this is there at Aspen Center for Physics. In addition to my experience with reading his lecture note and review article, I'm particularly honored by this award because I appreciate friendship and scientific exchange with my colleague and friends in Korea. As it was mentioned in the introduction, actually my first international scientific trip was to KAIST in 1987. This is actually a photograph from KAIST. This is where actually currently where the KIAS is located. I think the same campus as currently where KIAS is located. I've been to Korea many times, most recently in the KIAS review committee. I think Professor Hyojin Lee is here, I'm here. And with my friends in Korea, India, and China, we have been also organizing Asian Winter School. 2 years from now, to be held in Korea, and I look forward to that. I should also say that I have written various popular science books, and 3 of them have been translated into Korean. And this one seemed like has been particularly well received. This is actually a popular mathematics book written for high school students. And in fact, one more book is currently being translated. So I have lots of close friendship with my colleague and friend in Korea. So this prize is particularly, I'm particularly honored by this award. So now coming to the scientific part of my talk. So I would like to tell you about something about quantum gravity in the last 20 minutes or so. And so I would like to particularly tell you why unification of gravity with quantum mechanics have been so difficult. And so when you ask string theorists, this is a standard answer, that if you consider Einstein gravity coupled to finite number matter field, cosmological constant Einstein term, then this Lagrangian is not renormalizable in the sense that Benjamin Lee renormalized gauge field. And so therefore it cannot be used to calculate quantum effect. Well, this is sort of true, but it's not the whole story, because if you think about it, this is a Lagrangian for pion in nuclear physics, and this Lagrangian is also not renormalizable. F has a dimension of mass. But you can still use this Lagrangian to calculate various quantum effects quantitatively, as far as the energy scale is less than the value of F, which in this case is 184 mega electron volt. And in fact, you can calculate physical observable in the power of energy divided by F. And each term can be calculated perturbatively and systematically, and you can compare with the experiment. So this is actually a modern view of quantum field theory pioneered by Ken Wilson. So according to this Wilsonian point of view, this pion theory or any other quantum field theory that we currently work with are low energy approximation to some consistent ultraviolet complete quantum theory. And so these are derivable from ultraviolet theory by freezing low energy degrees of freedom. And so this is the idea of effective theory. So sometimes those low energy effective theory are non-renormalizable, but that does not prevent us from calculating quantum effect. And in the same sense, Einstein gravity is also an effective theory. So in principle, one might consider applying this Wilsonian view of effective theory. And in fact, there have been various successes in this approach. For example, the Hawking radiation from black hole, which I will come back to later. This is one of the very important observations and hint on how we quantize gravity, is based on the discovery of this effect is due to this effective field theory approach. The cosmic microwave background radiation fluctuation, which is one of the very important predictions of inflationary cosmology, is also calculated using effective field theory. So this is my favorite example. So suppose you have a Newtonian potential of 2 massive particles. So this is what we learn in undergraduate, right? A product of mass divided by length. But there are corrections. So there is actually a classical relativistic corrections. And then there are one loop corrections. And you can actually calculate this one loop effect by using effective field theory. This value 41 divided by 10 pi square. This coefficient is for pure gravity. And if you have electrons or other matter field, these coefficients are different, but you can actually calculate them. For expert, I should say that, well, you can actually calculate this because this is sort of coefficient of log divergence. But anyway, so there are some well-defined way of calculating it even though Einstein gravity is not renormalizable. But important question is that, is this really true? Does this Wilsonian idea work in gravity? And there are reasons to think that gravity is different from other field theory. That we learn in undergraduate course in physics that physical world has hierarchy of scales. That you have atom, and in the atom there is a nucleus and an electron. And if you open the nucleus, then you have protons and neutrons bound together by pions. And if you open up protons, there are quarks. So you have hierarchy. But there are reasons to believe that this hierarchy of scale terminates once you complete quantum gravity. One reason to believe that is that the existence of black hole. So typically when you collide high energy particles together, you can start seeing shorter and shorter distance physics. That's why we build a bigger and bigger accelerator to accelerate particles in higher energy, bigger and bigger energy, and make collision to probe short distance. But this does not work once you have gravity in it, because if you have very high energy, a black hole would form. And if you put more energy into it, the event horizon will grow and defeat the purpose of increasing the energy. So therefore, this standard idea of going to high energy to be equal to short distance does not quite work. And so this raises a question of whether Wilsonian point of view of low energy effective theory is valid with gravity. And in fact, there are reasons to believe that this idea of Wilsonian low energy effective theory does not quite work. That there are reasons to believe that if you randomly choose low energy effective theory with gravity, then it may not have consistent ultraviolet completion. So this leads to the idea of Swan Plant. So this is the kind of question that was posed by Qumran Buffer in 2005, that if somebody given an effective theory of gravity, how can you judge whether it is realized as low energy approximation to a consistent quantum theory with ultraviolet completion, such as string theory? So this question has been investigated greatly over the last 16 years. But I should say before I go on, that in fact, it was Albert Einstein who first raised this kind of question. And if you read autobiographical note, there is actually a very interesting quote where he points out that the low energy, any arbitrary low energy effective in the modern language, arbitrary low energy effective theory may not have a consistent ultraviolet completion with quantum mechanics and gravity. So that's sort of what Einstein says. So by now, there is actually a large number of Swan Plant conditions being proposed. Some very rigorous, and you can actually prove based on various assumptions about quantum gravity, and some are more speculative. And also, rigorous things tend to be rather useless, and powerful conjecture tend to be speculative, that as many things in your life, things tend to lie on this diagonal axis. So one of the aim of this program, Swan Plant program, is to push these things, to push these ideas towards this corner where it's both useful and rigorous. And so that's one of the things we are working on. But today, I would like to focus on things that we can prove so that I can complete my talk in the next 15 minutes or so. So first, these two conjectures I can in some sense prove absence of global symmetry and completeness of gauge charges. So I'd like to discuss those things. So first is the absence of global symmetry in quantum gravity. So symmetry is very important in physics, but it's very interestingly, there are reasons to believe that if you quantize gravity, there are no global symmetry in the system, that all global symmetries are either broken or actually gauge symmetry in disguise. So you can actually prove this rigorously if you use ADS-CFT correspondence. And this is actually based on my work with Daniel Harlow 5 years ago. And it's based on two ideas, locality, actually 2018. And this is based on two ideas. One is the symmetry being local, and this generalizes Metatherm. And the other is what's called entanglement wedge reconstruction. So let me try to explain those concepts. So first, Noether theorem. So Noether theorem is something we all learn in undergraduate physics, or maybe introductory, the first year in graduate course. That is that if you have if you have field theory or some physical system, and if you have conservation law, if you have a symmetry, then there is always some conserved charge which is generated by current. So you have a conserved current called the Noether current, and you can integrate this conserved current, the time component of the conserved current, over the spatial surface, and that gives rise to conserved charge, and these are called Noether charge. And if you quantize a system, then this Noether charge can be used to define symmetry operators. So in quantum field theory or quantum theory, if you have global symmetry, there is always associated unitary operator which realizes symmetry. So suppose R is a Cauchy surface, there is an operator, unitary operator associated to the group element and the choice of Cauchy surface. Now, suppose you divide this Cauchy surface into subregions, then this symmetry generator has a property that the symmetry generator defined on the union of these regions can be written as product of symmetry generators associated to each of these regions. So you have this kind of productivity, multiplicativity of this unitary operator. If you have actually Noether current, then this is actually obvious consequence of the Noether theorem. Because if you have Noether current, then U is the exponential of I times Noether charge. And the Noether charge is an integral of Noether current over these regions. So therefore, if you divide the region into subregions, into union of regions, Noether current becomes sum of current, Noether charge becomes sum of integral of Noether current associated to each of these regions. So therefore, if you exponentiate it, you get this identity. So this is the obvious consequence of Noether theorem. But in fact, according to the algebraic approach to quantum field theory, pioneered by Rudolf Haag and his followers, you can actually prove this rigorously even when you don't have Noether current, such as a case when you have discrete symmetry, for example. Suppose you have a finite group like Z2 or Z3 or monster group. This is still true. Okay, so we assume this. The other is an entanglement wedge reconstruction. So in ADS-CFT correspondence, it is assumed that everything that happens in quantum gravity inside of anti-theta space, this caricature is meant to be that inside of this disk is an anti-theta space, and the circle is a boundary where conformal field theory is located. Anything that happens inside can be described in terms of conformal field theory on the boundary. But after 15 years of research on ADS-CFT correspondence, we come to realize that there is actually a refined version of this statement, where suppose you consider some sub-region of the boundary, then you can consider some what is called the entanglement wedge area, which is defined as follows. Consider what is called the Ryu-Takayanagi surface associated to the boundary region, which is actually the minimum surface ending on the boundary of this region A. So if you have a region A, there is an associated Ryu-Takayanagi surface extending into the bulk of anti-theta space. And the famous work by Ryu and Takayanagi is that entanglement entropy for this region is calculable by calculating the area of this minimum surface. Entanglement wedge reconstruction says that if you consider this subregion, this shaded region sandwiched between Ryu-Takayanagi surface and the original region, then anything that happens inside of this region are encoded on this subspace. So this is the entanglement wedge reconstruction. Okay, so with these two assumptions, I can prove that there are no global symmetry in quantum gravity in anti-theta space. So the proof goes as follows. Suppose you have a gravitational theory in anti-theta space, and suppose it has a global symmetry G. So that means that there must be some local operator in the bulk that transforms faithfully into another local operator under this global symmetry G. Otherwise, the symmetry group does not mean anything. We can always assume that there is a bigger symmetry group as far as it doesn't act on anything. So in order for the global symmetry having global symmetry being meaningful statement, it has to act on something non-trivial. So therefore, we assume that the group, there is some bulk global operator that transforms non-trivially under this global symmetry. But that leads to a contradiction, as I'm going to explain now. Suppose we place such a local operator in the middle of this bulk anti-data space. And suppose you cut the boundary into segments like that. And so R1, R2 to R8 in this case. And consider entanglement wedge region for each one of them. So according to entanglement wedge reconstruction, anything that happens in this particular shaded region is encoded in this region R1. And anything that happens outside of this, you cannot tell from R1. And the same is true for R2, R3, etc. But now suppose you have this symmetry group G. Then the symmetry generator associated to this small g, which is an element of G, can be expressed as unitary operator acting, product of unitary operator acting on each of these regions separately. But each of these operator, UG of Ri, would commute with this local operator located at the middle of one space, because this operator, this point here, is not in this shaded region. Therefore, it should commute with any operator associated to R2. This does not belong to this shaded region, so that means that it should commute with any local operator associated to R3, and so on. So from that, we can deduce that any local operator associated to this point X should commute with a symmetry generator, which can be expressed in this way. But this contradicts with an assumption. So therefore, what was wrong was that we assumed that gravitational theory has a global symmetry G. So therefore, we have been able to prove that you cannot have global symmetry in consistent quantum gravity in isolated space. So this was what I published with Daniel Harrow in 2018 in 2 papers. One is a short summary appeared in Physical Regulators, and the other is a 35 times bigger paper, which just appeared in Communication in Mathematical Physics. So let me move on to prove the completeness of gauge charges. So simplicity, I'm going to discuss the case when gauge group symmetry in isolated space is a finite group. And this is based on my recent work that I just published last month. And so this based on the so I'm going to prove this in 2 steps. One is that, so since you have ADS-CFT, so you can calculate a partition function in conformal field theory. But not just calculating the partition function into the minus beta H trace, but insert some symmetry generator. I'm going to prove that this is actually equal to delta function of G times trace in when symmetry group is a finite group in high temperature. Okay, in high temperature it becomes like that. So that's what I would like to prove. So how are we going to prove it in quantum gravity? Well, we can prove this by knowing that in the high temperature limit, the dual of this partition function is a calculation of Euclidean black hole. So we can use Euclidean black hole in the bulk. So therefore, this calculation, the trace of e to the minus beta H with gauge group G inserted, is the same as calculating the partition function of Euclidean black hole with this symmetry generator inserted on the boundary, this unitary operator. So this is for high temperature above the Hawking page transition. So then we can do this manipulation by inserting Wilson line operator. In view of the time, I'm not going to go into detail of this operation. By manipulating this Wilson line operator, you can prove this type of identity for the twisted partition function. And then by using the standard completeness of characters or Peter-Weil theorem, you can prove that this implies that this identity. Okay, so this is sort of something from here to here is something you learn in undergraduate group theory course. And then we can use completeness of character of a group, which is another thing you learn in a group theory course in undergraduate. You can show that this twisted partition function can be expressed in this way. And this is actually a nice formula because it tells you that how you can decompose a Hilbert space of conformal field theory and therefore the dual gravity theory uncertain space in terms of the representation of this group. So we can see that each group is weighted by this factor. So this means that each representation alpha of the group occupies this fraction of all states. So, so this statement seems to be rather general, that this does not use anything like knowledge of gravitational action or any other dynamical interpretation. So this seems to be true regardless of what kind of gravitational theory we are considering. So this led us to conjecture that perhaps this is true for more general class of quantum field theory. And in fact, in 2D CFT, this seems to be true, that you can actually prove this without using holography. So perhaps this is true in more general. So this is something that I'm thinking currently. So in the remaining time, I just want to very briefly say the other conjecture, but this is sort of dangerous situation because these are conjectural. So for example, there are things like weak gravity conjecture, which says that the gravitational force is the weakest of the weakest force in nature, or there is a distance conjecture. And this conjecture leads to some non-trivial constraint on cosmology, in particular the cosmic inflation. And there have been various interesting work, one of which is my colleague at Kavli IPMU, Hitoshi Murayama. And in fact, this can in principle be tested because JAXA, Japanese Aerospace Agency, has recently approved the launch of the new satellite to measure cosmic microwave background radiation. And this actually tests the existence of cosmic inflation period in the early universe. And in principle, we can confront the observation with this prediction. So it can provide a very unprecedented opportunity for string theories to confront observation. So I think that before this satellite is launched, we should work hard to come up with predictions. So this is another thing that I'm currently interested in. So this is sort of this kind of Swan Plant conditions can lead to very interesting prediction of string theory. So I'd like to end this lecture by another quote of Benjamin Lee, but this one is actually the speech that Benjamin Lee himself gave on the occasion of Heinemann Prize of Steven Weinberg, his very good friend. This is Steven Weinberg, this is Benjamin Lee. And this was actually one of his last speech because it was given in January of 1977. So let me read it on this occasion. So Benjamin Lee, in one of his last speech, says that, do we understand or hope to understand weak interactions as well as, say, electrodynamics in the present framework, by which he means the renormalizable gauge theory with spontaneous symmetry breaking that he was working on. He said, perhaps we have yet to come to the grips of CP violation and ultra high energy behavior of weak interactions, on which subject I have a few remarks to make, but I'm more optimistic than ever that we are on the right track. And he was certainly right about it. So I'd like to end my lecture by paraphrasing his last sentence by saying that we hope to understand the gravity as well as his electroweak theory. Thank you very much for your attention.
Thank you, Hiroshi, for your nice talk. Now the session opens for questions and answers. So if anyone has any question, then please ask without hesitation.
Hello, Hiroshi.
Hi, good morning.
Congratulations and thank you for your very nice talk.
Thank you.
I have a very low level question. So you know that any, I guess, easily writable theory in ADS, I guess have a very big group of symmetry, right? The global symmetry, I would say. For example,
what do you have in mind? What symmetry do you have in mind?
for example, just the Lorentz group?
Oh, so these are gauge symmetry. So certainly there are conformal field theory with symmetries which has holographic dual, but in the bulk uncertain space, these are gauge symmetry because Lorentz, you said Lorentz group, but Lorentz group is a coordinate transformation. More generally, conformal field theory has conformal symmetry, but these are coordinate transformation. And so therefore, in the bulk theory, gravitational theory is general covariant. So therefore, these are part of gauge symmetry, but these are sort of non-normalizable part of gauge symmetry. So for example, in the electromagnetism, we have gauge symmetry, U1 gauge symmetry, but electric charge is conserved, right? And the reason for that is that electric charge is associated to gauge symmetry, which is not normalizable at infinity. So in my paper with Daniel Harlow, the reason that it took 175 pages is that we very carefully gave a definition of what we mean by global symmetry, which we prove does not exist, and gauge symmetry, which we do not, which we do not prove not existing. And the distinction in this case is that certainly you can have conformal field theory with symmetry, but these symmetries are all non-normalizable part of the gauge symmetry. So there are symmetries that have origin in gauge symmetry and symmetries that have origin in global symmetry. And we excluded only symmetries that have origin in global symmetry in the way that we defined in our paper.
So do you then consider only gravitational part, or do you want to include just meta sector inside?
This proof is valid for any consistent quantum theory of gravity. So it is true for, if there is a pure Einstein gravity, which has CFT dual, it can be applicable to that, but it's applicable to any gravitation theory which has consistent conformal field theory.
So let's just think about the simple, just abelian Higgs model, then the inside the ADS. So you have just U1 phase rotation, right? Which is not.
These are again gauge symmetry that is spontaneously broken.
I mean
you're talking about gauge symmetry still.
Okay, it is a still gauge symmetry. So
it's a spontaneously broken gauge symmetry.
It is right, but I thought that I can easily cook up.
No, you cannot.
Global. I mean, global symmetry.
Because I have proven otherwise.
Right. Okay. So far,
I challenge you to come up with example.
Yes. So
that
means that if we, so there is something wrong if we just wanted to consider just the global subgroup of
So you can write down low energy effective action in uncertain space. Say, for example, suppose you have 3 massless scalar fields with exactly the same property. Then there is a rotation symmetry of these 3 scalar fields. That is a global symmetry. That can be global symmetry. But I would say, based on our theorem, that symmetry is either broken by higher dimension operator if you calculate higher derivative term in the correction to low energy effective action, or in fact there is some hidden gauge symmetry which rotates these three fields.
So you say that if we consider just ON model.
Yeah, so this ON symmetry should be either broken or in fact gauge symmetry in disguise.
So
same thing happens in standard model. You know, so standard model of particle physics has B minus L symmetry. And we believe that this B minus L symmetry is either gauge.
Theory, there is no reason that there is, the ON symmetry should be broken, but here you are predicting that I
proved it. So there is a good reason that it should be broken or gauge. Or gauge.
Okay, thank you. Okay. So that's your prediction.
Well, it's not a prediction, it's a proof. It's a mathematical statement.
Anyway, the proof includes...
proof in this context.
There seems to be other questions.
Yeah, I think Jiawon has a question.
Yes, thank you very much for a very interesting talk. So I have like just two questions. So one of them is, so your proof is valid in anti-de-Sitter space. So what would be necessary for you to extend this to like flat space or de-Sitter space?
That's a very, very good question. And so this is very interesting question, especially first, we would like to understand whether this extends to flat space. And naively, you might think that, well, we should be able to do that if there is actually a series of uncertain solution where a cosmological constant is increasingly become small. Okay, so then whether we can take some kind of limit of this theorem to prove that gravitational theory in asymptotic flat space also have this kind of property. Now, but limit is actually rather delicate because it changes the causal structure in the limit. So we have to be careful. So I have not come up with a satisfactory, rigorous approach to it. There is actually a very interesting work recently, or maybe last year, by Daniel Harrow and his collaborator, where they actually used this idea of this proof, but put it in the context of a black hole in asymptotically flat space. And there they almost gave a proof that seems to work in asymptotic flat situation, although they have to assume some additional thing like island formula for black hole evaporation. But if you assume those things, they seem like there can be a proof that extend to asymptotic flat space. But it seems like you have some new ingredient to go beyond uncertain space.
Oh, that's very interesting.
Yeah, I think that I recommend you to take a look at that paper. I think that appeared sometimes last year.
I will. So the second question is that, so this statement about the absence of global symmetry is supposed to be, so like you might actually have in nature approximate symmetry. So that might be visible at some low energy scale.
Right.
So does this proof can say anything about like the scale at which this global, like absence of global symmetry being exact or?
Yeah, so this is another very, very good question. So there are lots of refinement of this no global symmetry conjecture. That's why I had this diagram. So there are new conjecture like weak gravity conjecture, distance conjecture, which in some sense quantify how symmetry. So I said that global symmetry should not exist. So it should be either broken or gauged in disguise. So for example, weak gravity conjecture somehow quantify how this is gauged, if it is gauged, for example. And it's very interesting to try to actually give some quantitative estimate of how strong the breaking happens. So I was just about to mention that when I was discussing this earlier question. For example, standard model of particle physics has B minus L symmetry. It's a global symmetry, but it's sort of accidental symmetry. You can show that if you assume particle content of standard model and Higgs mechanism, then B minus L automatically happens in low energy effective theory. But if you include higher derivative terms, you can write down terms that violate B minus L symmetry. So then it's an interesting question of how strong these additional terms, coefficient, how big the coefficient of these terms are, because this will tell us, for example, how the lifetime of protons. And so, for example, our friend in Kamioka in Japan are trying to measure the lifetime of protons. And so it would be good to give them some estimate of how big this kind of effect can be. So I think that refining this theorem by coming up with a way that you can quantify how strong the breaking effect can be is a very interesting question. And in fact, there are some good ideas about that in quantum information theory. So I didn't go very much into detail in my lecture, but this entanglement wedge reconstruction is very closely related to the idea in quantum information theory, in particular quantum error correcting code. And there is a relation between symmetry and quantum error correcting code, which is sort of quantum information analog of this statement called the Eastern-Kennel theorem. And then there is actually an approximate version of this Eastern-Kennel theorem, which I have an impression is related to a potential answer to your question. So I think that understanding this kind of idea in quantum information theory and quantum error correction can potentially inform us about this question of how symmetry can be broken. So I think that's another thing that will be very interesting to explore.
Thank you very much.
Any other question? We have time.
May I? So, I mean, when people begin to look at the Swan Plant issues again, of course, one of the issue was landscape and possibility or non-possibility of the
Right.
zeta universe. Right. Do you have some perspective on, broad perspective on that to share?
Yeah, so this is of course a very important question because it's related to both the inflationary model of early universe and also the origin of dark energy of our current universe, why the universe expansion is accelerating. And there have been proposed construction like KKLT, which claim to have constructed Dojita solution from string theory. Some people have questions about it. So there is a conjecture about whether such construction is possible or not, and if not, what's possible. So these are sort of rather vaguely called the Dojita conjecture. And as you can see in this diagram, the Dojita conjecture is sort of on this useful side because if it is true, then it has information on the nature of dark energy of the universe, but it's one of the most speculative side. And so certainly I don't claim that we have actually derivation of this Dojita conjecture, or but it is true that KKLT conjecture, KKLT construction was proposed already 2003, so that's almost 18 years ago, and it's still work in progress. So constructing a Dojita solution has certainly been a very, very challenging project in string theory. Well, it does not necessarily mean that it does not exist, but certainly I think we should, so this is what I said in my summary talk at the Strings conference this year, which is that both landscaper and Swan Planters are making bold claims. That Swan Planters are claiming that there are this kind of universal property of quantum gravity, and landscaper are claiming that, well, you have this tens of thousands of vacuum in string theory. Both are extraordinary claims, and I think that it's very important to scrutinize all aspects of these claims. And in fact, I think one of the scientific contribution this Swan Plant work has contributed is that inspire people to come back to scrutinize existing construction of Dojita space. And in fact, we have in the past 3 or 4 years, we have learned much deeper and much better about how possibly this kind of construction works. And it's possible that eventually this leads to actually more robust construction of Dojita space.
Okay. Any other question?
Yeah, I would like to ask a question.
Please.
First of all, thanks for your nice overview.
Right.
Some of us have been puzzled by the potential of the Swan Plant conjectures to say something meaningfully about the H-0 tension problem. Could you comment on this?
Yeah, so this is an interesting question. I have thought about it. It is not clear whether, yeah, so of course, currently it's a question about observation. But so I was interested to know whether, for example, if you modify the nature of dark energy of the universe from that of the cosmological constant, whether that issue can be addressed. But I have not come up with a good idea on how to do it. I think people must be studying this kind of question. But unfortunately, I do not have a sort of convincing potential theoretical scenario to address this puzzle. Yeah, I think this is a very interesting puzzle.
Okay, thanks.
Mm-hmm.
Can I ask also a question?
Please.
Yes, so I also join others thanking the inspiring talk. So my question is about the no global symmetry. And could you comment on the like S duality, SL2Z in type 2 supergravity, whether it...
So say it again, please. S duality?
Yes, SL2Z,
okay.
like...
Good. Yeah, so that's a very good question. So duality is symmetry in this kind of supergravity series. But these dualities are actually gauge symmetry. So you can actually have an example. For example, let's consider T duality. Suppose you compactify string theory on the circle. So then there is a T duality symmetry where R goes to 1 over R. I'm giving you some simpler example. We can talk about this duality. But let's consider R goes to 1 over R symmetry. So I would say that this is actually gauge symmetry for the following reason. So there is actually, if you change the radius, there is self-dual point where symmetry gets enhanced. So if you have just circle compactification of string, then you have a U1 gauge symmetry. But in the particular radius, you have SU2 symmetry. Okay.
Yeah.
And then if you go away from this self-dual SU2 radius, then SU2 is broken to U1, but it's sort of spontaneously broken gauge symmetry now. SU2 is spontaneously broken to U1. And one of the features of spontaneous symmetry breaking is that the broken part of the gauge symmetry now relate to different part of the modular space. And in this case, it's actually relate R to 1 over R. So therefore, you can see that T duality is actually the remnant of SU2 gauge symmetry that is spontaneously broken to U1. Okay, so S duality is the same thing. So there are S duality invariant point where symmetry is gauge symmetry is enhanced. And if you go away from that point, symmetry is spontaneously broken. And then S duality appears as an action of broken symmetry on the modular space. So therefore, S duality can exist in gravity theory in Einstein space. Because it is actually the spontaneously symmetry, spontaneously broken gauge symmetry.
Does it have a full generality that all the duality should be?
Yes, I think so. So I think that these dualities, well, I cannot say all the duality because there are like mirror symmetries and similar things like that, which are of different nature. So when we say duality, we mean different things. But for example, so if we restrict ourselves to say S duality or U duality of supergravity theory, if that's the kind of duality you are talking about,
yeah,
these are gauge symmetry in disguise.
Okay, thank you.
Mm-hmm.
Can I ask you one more question?
Mm-hmm.
So your global symmetry include the discrete symmetry
Yes.
also?
Yes.
So you think that the all time universal parity and so on all are either broken or
These are gauge symmetry again.
again gauge symmetry.
These are gauge symmetry.
So why let's say even the Ising symmetry is a discrete, I mean the gauge symmetry?
No, what do you mean by Ising symmetry? The Ising model has the two symmetry. These are global.
I mean just the 5-4 model, real 5-4 model, which has so these are all you mean
phi goes to minus phi symmetry?
Yes.
Oh, so if you, so depending, so you can actually have a prescription to think whether this is actually a gauge symmetry or global symmetry. But if you write down just this phi to the 4th theory coupled to Einstein gravity, then this Lagrangian has gauge symmetry, global symmetry where phi goes to minus phi, which should be either broken or gauge symmetry in disguise. And in fact, there's a way to think about this as a gauge symmetry too, which is then consistent. But then you can actually tell the difference. For example, you can have, you can ask whether you can have a black hole with Z2 symmetry or not, Z2 charge or not.
So you said that parity is also gauge symmetry.
Parity is a gauge symmetry because it's part of the diffeomorphism.
Okay, thank you.
Okay, here is question. Can I? So this is Young Bang, the president of APSTP.
Please.
And congratulations again. And thank you for your excellent talk. I have questions from outsider of this field.
Yes, please.
So you said you have proven there is no global symmetry in gravity, and
Yes.
From outsider, still I don't understand what's the physical meaning or implication of this property.
Okay, so one physical implication is that standard model of particle physics, you know that this theory of quarks and leptons
Right.
have global symmetry.
Right.
So it has a B minus L symmetry. The difference of baryon number and lepton number is the exact symmetry of standard model of particle physics. The baryon number itself can be broken in standard model by Sphaleron. So we may not say that it's a symmetry, but B minus L is preserved by Sphaleron. So it's an exact symmetry. But if you couple it to gravity, then this kind of theorem, or well, to be precise, I only proved it in unfit space. So Jaewon asked whether we can extend it to flat space. So I shouldn't say that my theorem predict, but it's reasonable to expect, as I was discussing with Jaewon, that this theorem can be generalized to asymptotically flat space case, in which case B minus L symmetry cannot be global symmetry if you go to higher energy. So that means that you have two possibilities. One is that in fact there are some hidden gauge field which mediate B minus L charge, B minus L symmetry, like photons or some other particles that mediate, that couple to B minus L current. That's one possibility.
Okay,
and another possibility is that if you go to higher energy, then you have to take into account higher derivative correction to the standard model Lagrangian, which can break B minus L symmetry. So one of these things happens. So there are some explicit prediction that this global symmetry in low energy, for example, if you have B minus L symmetry, the protons can be, does not decay. But then this would predict that there ought to be a mechanism where proton can decay.
Still, I cannot follow very well your explanations from outside of this field. So still, what's the implication to construct quantum gravity based on
So
your...
implication is that if you couple standard, if you consider standard model of particle physics, which we know exists, and we know that the gravitational field exists, gravitational force exists, we know quantum mechanics exists. So we have three things: element, standard model, gravity, and quantum mechanics. If you consider any mathematically consistent framework, it can be string theory or it can be loop quantum gravity or whatever consistent mathematical framework, to include all these ingredients, then the proton must decay.
I see. So you have some implication.
Yes.
Yeah.
So
Then,
we are trying to develop more implications. What I was saying toward the end was I would like to also derive some quantitative prediction about primordial gravitational wave coming from inflation period. And there is a potential way, potentially there is a way to have some quantitative prediction about the strength of these primordial gravitational waves.
Okay,
and this is sort of currently ongoing project.
Yeah, thank you very much. And I have also another question from outsider. So you can say quantum gravity is on the right track in the progress using string theory, or you need to completely, do you think we need something completely different framework?
So this is a philosophy on how you do the research in theoretical physics. I follow the example of John Wheeler, which is radical conservatism, which is that if you are given with some theory, you try to use it to the extreme until it's broken. So string theory seems to work very well in helping us understand many deep aspects of quantum gravity. And it has led us to this holography of quantum gravity, which has been very, very fruitful in developing insight into quantum gravity, but also connecting these research to a variety of other areas in theoretical physics, such as condensed matter physics and quantum information theory. So certainly, it has been a very fruitful direction. And most recently, holography of quantum gravity has gave us very important insight into how Hawking's black hole information paradox can be resolved. So ADS-CFT correspondence in principle show that Hawking's original prediction that the black hole evaporation process destroys quantum coherence is wrong. But we have not, the earlier work did not explain how information comes out from black hole. Now, over the last couple of years, thanks to holography in quantum gravity and many other insights, we are beginning to understand how this information comes out. So certainly there have been lots of very strong progress in understanding quantum gravity using string theory inspired ideas. So compared to that, other approach in quantum gravity has not produced any important insight into these kind of questions. So certainly, I think that as far as this progress continued, it seems very worthwhile to investigate along this line.
Okay, thank you very much. And congratulations again for your award.
Thank you.
Okay, thank you again, Professor Oguri, about your excellent lecture. And I also thank to all the audience about enthusiastic participation. So before finishing this session, I have two announcements. One,
Sir, I'm sorry, but there's another question here, if you don't mind. Is that okay?
please.
Yeah, okay, so just one small question. So you did everything in ADS space, right?
Yes.
So yeah, it's conceivable that you take the length scale larger enough and you really generate the Minkowski space. So I mean, your result should in principle be also valid for flat space, or is something breaking
so
down?
This question is very much related to the earlier conversation I had with Jae-won. That is that so namely that Jae-won asked whether we can generalize our proof to asymptotically flat space, because that's the more interesting from physics point of view. And I have been thinking very hard, try to see whether we can take appropriate limit of our result to actually give you a rigorous derivation of similar claim in asymptotic flat space. I have not been able to do that to my satisfaction. You are quite right that one way to take the limit could be to focus on some finite region in isolated space and somehow go to low energy limit and take some almost flat space regions. And but it's kind of hard to give some precise quantification of observable in such an arrangement. Maybe there is a way of doing it. I have not been able to come up with a rigorous way of doing it. I think that at variety of level of rigor, so it seems to be that it's very likely that there ought to be some limit where way of taking limit where you can derive some result in asymptotic flat space case. But no, I have not been able to do that yet. So yeah, but anyway, so this is one of the very potentially interesting directions to pursue. I agree.
Okay, thank you.
Thank you. Okay.
Can I also ask a question? So your proof doesn't work if you have a charged black hole in the center of ADS, right?
Why is that?
Because of the second criteria that you have this error correction. If you cannot put any operator in the center that is.
So when you talk about charged black hole, these charges are gauge charges. So you know that there is a famous theorem in general relativity called no-hair theorem. Black hole can only have three kinds of parameters. One is mass, the other is angular momentum, And the third is a charge associated to gauge symmetry. So these charges can be like electric charge, which is associated to abelian gauge field. You can also have discrete gauge charge, called these are discrete hair, these are called discrete hairs. Those are studied by Frank Wilczek and collaborators in the early 90s. So black hole can have these charges, but these are gauge charges. On the other hand, if you have global symmetry, black hole cannot be charged with respect to this global symmetry. So black hole doesn't have global hairs in some sense. So therefore, the existence of a charged black hole does not contradict with my theorem, because the charges that you are talking about is again gauge charges, not global charges.
So even if I have a big black hole, I mean, just a big black hole that just asymptotically is ADS. You cannot, I mean, it covers most of the bulk.
Yes. So you are considering the black hole whose horizon is of the order of the size of the ADS radius.
So your proof probably doesn't work, right?
No, I don't think so. Why do you think so?
Because it's already covered, like most of the bulk is already covered by black hole. And so when the rest can be reconstructed by the boundary, I think.
Yes.
So the second criteria of your proof, I think, has problems when you have a big black hole. I know.
Well, we can choose this region to be as small as I like. So you can have a big black hole, but I can make the region to be even smaller. I think somebody has to mute. I think that Taejong Park has to mute himself.
이거 좀 뮤트 시켜주시죠.
Okay, so probably there are lots of other questions. But,
yeah, I'd like to answer this question. So this is important,
sure.
but somehow somebody.
아니 오늘 사실 원래 경주 갔어야 됐는데.
국장님, 이거 뮤트 못.
Okay, so let me answer that question because it's an important question.
이것들 정말.
It's an important question, so let me answer that question. So the person was asking, suppose you have a big black hole, then the region, it can go very close to the boundary, so how can my argument work? So what I can do is that, suppose you have a big black hole, big but finite black hole, then there is still some finite distance from the boundary. So then I can make this sort of division of the boundary into segment. I can make segment as small as I like. So I can always win. I can always make this region smaller than the size that is remaining after you that was eaten up by black hole. So as far as you can consider black hole with finite energy, if you consider black hole with infinite energy, that's a different thing. But then you cannot make a good argument in that case. So if you have a black hole with arbitrarily large but finite energy, then I can always arrange my argument so that it still works.
Okay.
Thank you.
Okay, thank you very much. This is time for two announcements. One is photo session awaits you. So please turn on your camera. I would like to ask all of the audience for photo session to make a history. And second one is
well, it's nice to see those people. Yes, all the audience. Thank you.
Please take a picture. I would like to ask APCTP to take a picture.
Hi, Monica.
네, 다들 please come to the front and we'll have a 네. 네, 알겠습니다. 그러면은 다 같이 please look at the camera and we'll take a quick screenshot. Okay. 1, 2, 3. 1, 2, 3. Thank you.
Thank you.
Okay, yeah, now second announcement. Before finishing this session, as shown, please show APCTP, please show us the page for Hiroshi's 2 lectures. Okay, as shown on the screen, there will be 2 lectures from Professor Oguri about physics and mathematics of the Calabi-Yau manifolds. So please join these lectures also on November 1st and 2nd. And then I strongly hope many of you will participate and also encourage the students near you. So now the session ends. So I hope all of you will enjoy other KPS talks in this form. Thank you very much again, all the audience and Professor Hiroshi.
Thank you.
Those are very long questions answers.
Well, it was
an
good. I was
important
worried that
topic.
there may not be many questions.
Yeah.
Hi, Seo-chan.